Lesson 6.1, Exponential Growth and Decay. Our essential question, how do you graph exponential growth and decay functions? There were 2 problems left for independent practice. Let's take a closer look at those. So we're looking at another car where Y does represent thousands of dollars, and it said it can be approximated by using this model. T is still the number of years after we've purchased the car. So first question, is it an exponential growth or an exponential decay? We find that by identifying B. B is the value always with the exponent. My B is 0.9. Because B is between 0 and 1, I know this is going to be an exponential decay. Which means in question number 2, we don't want to identify the increase, we want to identify the decrease. So identify the annual percent decrease of the car. Well, our decrease rate is the equation 1 minus R, but our decrease rate is also the value of 0.9. I want to know what is my rate, what is my R. So I'm going to go ahead and solve for R. And I found my R to be 0.10 as my decimal, but you had to convert that into a percentage. So 10% is my annual percent decrease. Now we're going to use Desmos, and we want to find when is this car going to be worth $8,000. So here's my XY axis. We know it's a decrease model. The Y value is going to represent the value of the car. And we know the X value represents time. We are looking for a Y to be around 8 because the value of the car is in thousands. So I'm looking for when is my Y as close to 8 as possible. So typing this function into Desmos, we get our point to be about right here, and that coordinate point is the coordinate point 10.8, comma 8.012. This is the closest Desmo gets me to a Y value of 8. So this is my Y value saying I'm close to about $8,000. This is my time in years. So my final question, estimate when, so my when is 10.8 years. So the value of the car is about $8,000 about 11 years after. Our last problem. We're talking about bacteria now instead of cars. The number of bacteria in thousands in a culture can be approximated by this model here. T is going to be the number of hours in the culture. So T is going to be hours. First, represent growth or decay. We represent growth or decay by identifying B. B is the number with the exponent. My B is 1.99. Because B is bigger than 1, we know we are going to have an exponential growth. So question number 2, I don't want the decrease. I need to know my annual percent increase. The annual percent increase is the value 1.99, but we know it's also the formula 1 plus R. So I need to solve for R. Subtract 1 from each side. I get R to be the decimal 0.99, but you need the percent. So this is 99%. So I need to use Desmos to find when will the bacteria be 1 million. So here's my estimated graph from Desmos. Because we are growing, we know our growth is going to look like this. The Y is supposed to be number of bacteria. It's the number of bacteria in thousands. So I'm looking for the Y to be about, 1,000 would have been here. So I'm looking for 1,000 1,000s. And my X is going to be time in hours. So we drew an exponential growth model, but this was just a general growth model. When we looked at Desmos, our bacteria growth model hugged the Y-axis so incredibly close that it needed to look like this instead. So I was going along the Y-axis, and I was looking for when my Y was 1,000. And I found this coordinate point, 3.347, really close to the X-axis, and close to 1 million. This X value right here is my time in hours. So when did I reach the 1 million bacteria count? About 3.3 hours. So the bacteria count's about 1 million after close to 3 hours.